Hi, this is Ed Blumdahl again, and I've made several of these YouTube videos concerning physics, astrophysics, astronomy, cosmology, even though they're not directly mentioned, but it covers all of this. And today is another topic, which is rather big, but I had to pare it down a little bit. So maybe at a later time I could do something more on it. But the title of today's video is Photons in the Visible Light Spectrum. So, and I have underlined visible because at this point in time, all I really have looked for is what happens with visible light. The electromagnetic spectrum is quite large, and what I talk about here may or may not be applicable to radio waves or higher frequency waves. So just understand that when I talk about anything that goes on here, I'm talking about visible light spectrum from red to violet. So if we look at the top, so let's get started and we'll go through this. So as we look at the top, there are three lines showing a waveform, A, B, and C, and there's also a line pointing out what we consider the wavelength, right? The speed of light is equal to, at least current thinking, the speed of light is equal to the wavelength times the frequency. So we know that in the visible spectrum that currently red has fewer waves per unit, and of course violet has the most. So you can see it represented here in different wavelengths over to the left there, A, B, and C. The photons, are simply these little black dots that you see here, and they are throughout the three A, B, and C lines of light there. So currently, so what do we do? Well, currently, if the speed of light A, speed of light A, speed of light B, and speed of light C, right, denoted by the letter C, are all equal and fixed, and if there are three different wavelengths, that we're looking at, and they start from over where the S is by photons, they travel to this line T for time, what we'll notice, they won't arrive at the same time. In other words, it's nothing magic here. It's basic logic in a sense, where you have waveforms, right? This has fewer, this has more, this has the most, but this one is stretched out. You'll realize it has the longest distance to travel because it's traveling back and forth more than this or this, so that they'll never be equal. It turns out, if you think about it, that there is no combination of C and lambda and time that you can work out to make any of these work. You can change the speed of light, so to make up for the longer distance, this has a higher speed of light, this less so, and this even less so, right? And then it might work out where they all come to the T line at the same time, but then the constant speed of light is not constant, and obviously there's a problem there. This is where it stands. This is what's given as our understanding of light. It travels in waves, and it has a wavelength and it has a frequency. The problem that arises, there's no combination where you can keep the speed of light constant for all these different, what would amount to colors, right, and still arrive at the same time. I think this is maybe one reason why Newton thought there was, something was going on with red light, that the speed of light, actually red, might be slower. I don't know. I'm not really sure about that, but maybe it can be experimented. I don't know. But the problem is basically the waveform, right? The waveform that goes up and back like that. Now, this was, if you go back and look at the literature and the history of science, they had a waveform that is how they think that light propagated through space, right? There was this luminiferous ether, sort of like physical fog or something, that pervaded all of space. It's sort of like if you've ever seen pictures or video of a snake or a rattlesnake that's going through the desert and just sand, or find another snake that's going through the water, this undulating back and forth. That's basically how they thought light passed through this luminiferous ether. Of course, in fact, Maxwell's equations are all based on waveforms. So that's what they thought, right, this luminiferous ether. They needed that to have the photons. Well, it isn't. It's not there. The Michelson-Morley experiment, I thought, was the biggest failure that experimental physics has ever made, so there's a lot of problems. There is no luminiferous ether, okay, we know that. Albert Einstein and the special relativity, although I completely disagree with the whole theory as it is, at least he did one thing, or one aspect correct, and that was to get rid of the luminiferous ether. So I think Einstein was the first to sort of break the idea that we had this in space. And I know they've come up with frame dragging, but I think basically with frame dragging, they basically have bupkis. It doesn't work, right? So that's another problem, but maybe talk for another day. I look at it like this, what they're going now. You have a wavelength, right, going from A over to E here, right, a wavelength, and you have a waveform, right? This is the waveform, this curvilinear line here. And it turns out, I mean, this, when you look at it, if you're looking at the wavelength, it's this right here, but no matter how you use the change in waves, it'll never work. That's what we just pointed out. So what's your other solution? The other solution is that you project, the wavelength down, and what this becomes is nothing but a straight line, right? Because we know over here what I put is, the space or the curvature segment from AB to BC, CD, DE is greater than what? AE. That's why it never works, and it will never work. And I'm going to go into this a little bit more. If we leave it now, we have the waveform is greater than the wavelength. Even though they are at the same point, right? Obviously a straight line versus a wave, there are two different distances that they have to travel. The only way that you can get that is if you project down onto a line segment here, still A, right? Over A and B, over here, A and E, I'm sorry, over here, and light what? Light travels in a straight line, right? We don't need the luminiferous ether, and we don't need the curvilinear lines anymore, because it doesn't work. The only solution, right, that you can get this is if light travels in a straight line, right? Newton's first law of motion, basically. So light travels in a straight path. It doesn't travel in any type of waveform. Why? Because nature is efficient. Nature's had, as we think about, 14 billion years to work it out, and it has. And light does not need luminiferous ether because it doesn't work. It's not there. It just travels in a straight line. The shortest point, or the shortest distance between 2 points is a straight line. And life definitely knows that. But you still have to calculate one other idea. That's A to E, and we can't call it like a wavelength or a wave. We can't. I just call it S for space. You still have to account for that space what? Between the photons. I just call it S for the time being to get away from the wavelengths and whatnot. So what do you get from this? The way we're looking at it now is wrong. And what we have to do, and we've shown that the luminiferous ether doesn't exist. Einstein pointed that out. Maxwell have his wave equations right here. But in truth, light does not travel in a wave. It travels in a straight line. And you can see the reason. It's basic logic. Right? So that's what I want you to get out of this. Light travels in a straight path following Newton's first law of motion. Why? Because nature is very efficient. So I think I've covered most of that. What else can we do? Changing screens here, the old-fashioned way. Here you have a situation where I just sort of mocked it up a little bit. In other words, if you were looking down on this top diagram here, if you were looking down on this, like two racers, 1 and 2, they both had the same speed, right? They started from the same point, they had the same speed, and they're headed to the finish line over here. Now, once the gun was fired and they go, I mean, it's known that the one with the straight line is going to finish first every time, right? The runner who takes a diagonal or zigzag path is going to lose every time. It's a basic idea, right? Again, I mean, nature isn't going to do this. There's no reason for nature to travel in a wave. Light does not have wave fronts, which I'm going to talk about in just a little bit. But the only way, the most efficient way to get from that point to that point is a straight line, and that's what it does, right? Okay, so that's sort of tied into that. It's just an easy way to see. This is an easy way to see what's going on up here, comparing a wavelength path or zigzag path to a straight path. Nature will take this path, right? It's just another way to look at it. Now, here's sort of another aspect about this. Most people know, anybody studying physics or related sciences knows about Thomas Young and his double-slit experiment. He was quite an interesting person. I read a book on Champollion. Who was the person that really sort of put together the complete understanding of Egyptian hieroglyphs. But Thomas Young actually did a lot of the legwork to build a base on hieroglyphs from which Champollion used to finally make a full understanding of how they work. So he was quite a fellow, Thomas Young. And this is basically the way the situation is set up with this double-slit experiment, right? You have